What's good, y'all? This is Savad. Welcome back to my YouTube channel, to a new video. Today, what are we talking about? I decided to do something that probably is bad for my engagement, but talk about engineering. In Aero, you have what we call the Bernoulli Principle. That's an N, okay? Please don't judge. Yes, that's my chair. That's my whiteboard. Are you gonna judge? Yes. Do I care? Maybe. Okay. So, Bernoulli Principle. Why is this important? Listen. Listen. In aerodynamics, what produces lift, this is very out of scale. Okay, please. What produces lift is a pressure differential. So, delta P. P for pressure. Okay. So the pressure differential will create lift, a force acting up. In cars, you want that lift to go down. So let's say I have the opposite, different airfoil that cambers like that. I will get a force that goes down called downforce that we're gonna go call FD, okay? Force down. Don't confuse it with drag, okay? We're not gonna talk about drag, a little bit, but not really. So that pressure differential will cause lift for airplanes, downforce for cars. An airfoil is sort of a profile, a sort of device that allows you to generate lift. And we're not going to talk about fundamental flows, etc. So let's say I'm doing downforce. Conventions, okay? Nomenclature, FD. This is caused because you have a higher pressure on top and a low pressure on the bottom. For planes, it's the opposite. Essentially, this low pressure kind of creates a vacuum that will naturally push the car down because higher pressure wants to go to lower pressure. It's kind of like how you want to talk to that girl, but you never go for it. Okay. Essentially, the bottom will achieve, and I will tell you right now, the bottom part will achieve higher velocity. The top part will achieve less velocity. Why is that? Bernoulli Principle. Essentially, in pressure, you have, let's say I have that same airfoil, but only a part. Essentially, air right here will reach a stagnation point, a stag point. A stagnation point is, let's say the velocity goes nearly zero. Following? Hopefully. It's kind of like having a wall and you have the air just like hits it. Virtually, we can assume that its kinetic energy or velocity is gonna go to zero. Here, you will have the total available pressure to the system, okay? That total available pressure typically is gonna be equal to static plus dynamic pressure, okay? Both are two types of pressure in aerodynamics. Essentially, static pressure is whatever is in the ambient air. So ambient fluid or air in this case, because we don't care about water. Yeah, I don't care about water. Ambient air will have a natural pressure that's called static pressure. That's what's around. It's not really moving. We're assuming that it's not moving. And then velocity or moving air will also have pressure. It will have a pressure that will apply to contact or at a point of contact. Okay, based on this, hopefully you're still following, we have the following relation from Bernoulli that static pressure plus dynamic pressure is equal to a constant. Wow. What is that constant? Pretty much about the total pressure. But yeah, there's a total pressure available to the system, static pressure plus dynamic pressure. What Bernoulli did is he kind of like mechanical energy or potential energy. Essentially, that's the entire thing that is available, like mechanical energy, ME. That's our kinetic energy to the system, and that's our potential energy. Those two balance out to give total pressure, kind of like mechanical and potential and kinetic energy. It's kind of derived the same way. I'm not going to go through the entire derivation. I didn't fall asleep, but I was having a hard time following in class. Or like my professor was goated, and he was a little too good at math. So remember, static plus dynamic is equal to total. So he said that the pressure of air plus 1/2 rho v squared is equal to P naught. Following? P naught is going to be our constant. That's going to be the total energy available to the system, or total pressure. Now, in incompressible flow, you assume that density is constant. Because for low speeds, density typically stays constant. Honestly, I forgot why. But it stays constant, okay? Remember that. So density stays constant. So Now let's go to Venturi effect and wind tunnel. Venturi effect and wind tunnel. So for the Venturi effect, one thing that you have to know, a formula that you have to know is in the tunnel, I'm gonna draw a wind tunnel, but any kind of tunnel, let's say that's state 1, that's state 2, and that's state 3. The relationship between the air density at state 1 with its cross-sectional area at state 1 with its velocity, the air there, is equal to rho 2 A2 V2, which is equal to rho 3 A3 V3. Because it's incompressible, rho 1 is equal to rho 2 is equal to rho 3. So I can cancel all those out. I get my area at a certain point times my velocity at a certain point is equal to the area at another point and the times the velocity at that other point. Capiche? You following? Are you following? Okay, so let me rewrite Bernoulli, P plus 1/2 rho V squared. And let's remember this one, okay? So from this, with a constant, from this, I can derive that if velocity increases, pressure decreases, vice versa. Can you see where I'm getting at? Ooh, big, big, big. Using this, we know that A1 V1 is equal to A2 V2. If the area increases, so if area increases, velocity decreases. And vice versa, if area decreases, velocity increases. So essentially, let's take the example of a wind tunnel. That's my test section. That's my throat. That's my diverging section. And that's my converging section. The smaller my area, the faster will I accelerate the air. Conversely, my area is expanding, so my air goes down. That throat section is the smallest area. That's where the velocity vector is the fastest. That's where the air is the fastest. So that's where also the pressure is the smallest. All that leads you to ground effect in a car, or downforce generating in a car. Ground effect in aviation kind of follows the same principle, however, it doesn't have the same kind of usage. Ground effect in F1 or any kind of car is a downforce generating event. Because let's say I have my car, that's my wing, let's say that's an F1 car. Okay, what, that's a side pod. Hey, not bad, bro, not bad. Okay, in here, I want to have channels in that side tunnel. I want to have a channel that will channel air in and out. That's my diffuser, that's my inlet. In my diffuser, I will guide air out. In my inlet, I will suck air in. This entire section, I want to accelerate air. This section, I don't really care as much, but it's important for generating downforce because you don't want a stalling event. So you want to avoid stall. Important. You want to avoid stall. And I'll explain stall. That's my throat. That's the fastest area. Okay. So with all that, I'm trying to achieve low pressure, and that's what we call ground effect in F1, is we're using the ground as the bottom part of that wind tunnel or that Venturi tunnel. Lastly, let's talk about stall. Stall is when your airfoil, that's your air, when your airfoil has a flow separation right here. Here it does the same thing. Here the flow separates. That's your angle of attack. When flow separates, it turns back, causing what we call pressure drag. Pressure drag is because that low pressure and that high pressure meet very quickly on the chord of that airfoil. So you want to avoid stall or a stalling effect all the time, because that drag is a lot of drag comes from stall. That's how aircraft lose all their speed and the pilots freak out and everything. So that's basically it. Why am I talking about this? Why? Because I'm designing a side tunnel and a floor. That's what the floor of F1 car does. God damn it, you're following or not? Typically, F1 has a lot of speed. For FSAE, your air does not come in at a lot of speed. So what I'm trying to achieve is I want my inlet to I want my side tunnel to look like a wind tunnel. But right here, I have a problem. In my inlet, I have a lot of stag pressure. My throat is actually very good. My diffuser could use some modifications. It's a side tunnel. And so essentially, the wind tunnel that I have right now has a lot of stag pressure at the front, both of them, both of the iteration, has very good velocity in the throat, has a decent diffuser section, I could improve it, and also something that I didn't talk about was inwash. It has a lot of inwash. So I need to take care of that too. One way I could do that is by improving the area of the throat, letting a little less air in on its vertical, and I could also smoothen out the front wall. So that's a way to do it. That's what I've been trying to doing. Right now my floor has a good aero efficiency, so it's for my aero nerd out there, its LD ratio or CL CD ratio is about 7. So for 7 unit, and that's a standalone. For each drag that floor produces also 7 units of downforce. I know it should be negative or something, but drag is opposite. My lift is down, so it should be 7. So yeah, essentially that's where I'm at. That was a crash course on aerodynamics. I hope you enjoyed it. I'm gonna do a lot more of those just because it's important to me and it's something that I really like and enjoy to talk about. It's super simple at the core to understand, but then the math gets complicated. So that was it for today. You have a wonderful rest of your day. Please smash that like button, subscribe to my channel, turn on notification, and I'd say I'll see you for a new video next week. Oh my God, that was so bad. And I say I'll see you in the next video. Peace out.